Hello guys and girls, today we're going to be looking at proof by contradiction. This is a nasty part of the A-level syllabus, and today we're going to take a look at a couple of key proofs, especially from the OCR curriculum, but nevertheless knowing these is helpful for all A-level students. So the first one is the proof that root 2 is irrational. Now the main thing here is that when we do a proof by contradiction, we assume the opposite. So in this case, we're going to assume that root 2 is a rational number. Now we're going to take a little look at the definition of a rational number. The definition of a rational number in this case is that it can be put as a fraction, a over b, where a and b are integers with no common factors. Yeah, forgive me, I'm a slow writer. There we go, with no common factors, right? And we also need to specify that b does not equal to 0, because obviously if we have a divided by 0, then that is an undefined function. So now that we've made this assumption, we're now going to say that a over b is equal to root 2, essentially assuming that root 2 is a rational number. And we're going to do some manipulation with this. So first we're going to say 2 is equal to a squared over b squared. That's because we've squared both sides. And then we're going to multiply both sides through by b squared. So we get 2b squared is equal to a squared. And what's interesting about this is that because we have a squared is equal to 2 lots of something, then this proves that a squared is even. And this in turn means that a is even. And what this means is that because a is an even number, we can represent it by our standard sort of algebraic definition of an even number, which is to say that a is equal to 2n. And now we're going to substitute this back into our equation. So we're going to come back over to here now. I'm going to say 2b squared is equal to 2n, because a is equal to 2n, all squared. And now we're going to expand out the brackets. So we're going to have 2b squared is equal to 4n squared. And once again, we're going to divide through by 2. So we're going to have b squared is equal to 2n squared. And by the exact same principle as before, we've got b squared is equal to 2 lots of something, which means b squared is even. Bear with me. B squared is even, which means that b, hold on, just making sure you guys can see what I'm writing here. It means that b is even. There we go. And because we've now proved that a is even and b is even, then this means that a over b, just going to bring page over here a bit, is not fully simplified. In other words, as we assumed right at the beginning of this question, we said that a and b are integers with no common factors, and we've just proved that 2 is a common factor, which means we've contradicted our original statement. The logic behind a proof by contradiction is that as soon as you contradict any kind of assumption that you made at the start of the question, then this proves that the opposite must be true, because we've contradicted, one of our assumptions. Like this was the only thing that we assumed to be true. Somewhere the logic has broken down, and therefore, by result, the opposite must be true. And the opposite in this particular instance is prove that root 2 is rational. So I'm just going to put therefore, by contradiction, root 2 is irrational. And we're just going to put a little square here. You could also do QED. You don't need to do both of them. A couple different ways. They're just little symbols that we use to say we have concluded our proof. Now we're going to look at a second proof here, which is to prove that there are an infinite number of primes. So again, we're going to take the route of proving by contradiction, which means we are going to assume there is a finite number of primes. If there is a finite number of primes, then this means it is possible to list all of the primes, albeit it would probably be a very long list, but it's going to look something like this: P1, comma, P2, comma, P3, where P is kind of representing a prime number, right? I'm going to go all the way to the end to Pn. And that's our list of all of the prime numbers. That's the list of finite set of prime numbers, because there is a limited amount, right? So now when we scroll down a little bit, make sure everyone can see the page, we're going to imagine this number. We're going to imagine this number here. In case it isn't clear what I've actually written down here, I'm essentially saying P1 multiplied by P2 multiplied by P3 all the way up to Pn. In other words, multiply every single prime number that exists all together. So now you've got a number that is basically every single prime number multiplied together, which means it has every single prime number exactly once as one of its factors, right? And now let's assume that I add 1 to this number. So this now means, if you think about this logically, it cannot be divisible by any of the prime numbers that we've already listed, because the smallest prime number is 2. And if, say, we take a number that is a multiple of 7 and we add 1 to it, we know that that new number is not going to be divisible by 7. And the same rule applies to every single number in existence, except for, of course, 1. So this means that this number here has a remainder of 1. But more importantly, this number does not have any of the other prime numbers as a factor, and it is also not in our finite list of primes. It is effectively a new prime number. That's one option. New prime number. The alternative is that it is a composite of 2 other prime numbers, but the 2 prime numbers that it's a composite of are also not in the list. Either way, what we have here is we have a new number that is prime and is not part of our finite list. And therefore, this contradicts our assumption and proves there are an infinite number of primes. Those are the 2 main bases I wanted to cover today. In the exam, you can see lots of other different proof questions. Many of them will use similar methods that we've just looked at in these 2 questions. They'll involve these kinds of algebraic manipulation that involve recognizing that an even number can be represented as 2n, or an odd number can be represented as 2n plus 1. And then it might involve squaring them, or it might involve understanding the definition of a rational number, or understanding the definition of a real number. Those are the sorts of things that it's going to be crucial to understand if you want to bag these proof marks in the exam. And the proof marks are top tier questions when it comes to the exam. These are the sorts of questions that are going to get you your A star when it comes to the exam paper. So really, guys, this is some time. Honestly, these two questions right here, they're like things you want to just learn inside and out, like have them rehearsed and like memorized, right? And then you can apply the strategies to other sorts of exam questions that you'll face. But that's everything for today, guys. I hope this video has been constructive for you, and have a good rest of your day.